So welcome back. In this video, we are going to continue talking about waves on strings. And the first thing I want to address is that in the last video, when I was making waves by moving this wrench up and down in the simulation, you saw these wave pulses traveling along, and they were kind of localized regions where the string went up and then down, and that just moved along the string. And there was only one of those, and then I made another one. And so it wasn't the classic kind of shape of a wave that we normally think of when we think of ocean waves or other kinds of pictures of waves. And so the first thing I want to do is show you how we can actually produce those kind of classic looking waves, thinking about, again, the same simulation of a string where I can control one end of it. So let's have a look at this simulation. And so let's try to understand how I would produce one of these waves, like the ocean waves that keep coming and have repeating crests. And so the way to do that is basically just to take that wrench and then move it up and down in a periodic way. And so that's what this oscillate button does here. So this makes the left-hand side go up and down in simple harmonic motion. And what you see is that actually produces a wave whose shape at any time is this nice sinusoidal function, just like our time graphs. But now this is not a time graph, it's just actually the picture of the wave at a certain time. Okay, so now let's talk about some properties of these very special kinds of traveling waves that we call sinusoidal waves. Okay, so these are waves which are caused by some simple harmonic motion at the, say, in this case, moving the end of the string up and down in a periodic way, but more specifically in a way that is a simple harmonic oscillation. And so that produces a wave whose shape is also the shape of a sinusoidal function. So let's talk about some properties of these waves. The first one is just the amplitude of that wave. That's very similar to the idea of amplitude for an oscillation. Here it's just the maximum amount that the various points on the wave are displaced from their equilibrium position. The next thing is the frequency of the wave, and that's exactly the same concept that we had when we were talking about oscillators. If you look at how quickly this point on the wave, the place where I'm holding it here, goes up and down, so that is the frequency of that oscillation is what we would call the frequency of the wave. And that's the same as the inverse of the period, just like when we were talking about oscillation. So how long it takes that point at the left to go from the top to the bottom and then to the top again, that would be the period. The frequency is 1 over that time. So one thing I want to point out is that you could look at any point along this wave. So let's say this point here in the middle, and we can think of what happens as this wave travels by. Well, that point also is going to go up and down and up and down and up and down. And the frequency of that oscillation is just the same as the frequency of the oscillation at the left. And the reason is that basically this oscillation at the left is driving the next little part of the string to go up and down, and that's driving the next part to go up and down, and that's driving the next part. And so all of those oscillations have a particular frequency, and then they're causing oscillations in the next part with the same frequency. So the next thing we have is something that we didn't have when we were just talking about single oscillators. This has to do with the spatial properties of the wave, and it's just the rate at which the crests of the wave travel from left to right. So we saw that the sinusoidal shape in the simulation was just moving at a constant velocity. And that's what we call the wave speed. Okay, so the wave speed is the speed of any crest or trough in the wave as it moves along. The final property that I want to talk about is something that you can see at any particular time if you just take a picture of the wave, and it's the wavelength of the wave. So in this slide, there's a picture of a wave at a certain time, and the wavelength is just the distance between one peak and the next peak, or between one trough and the next trough. Okay. That's usually denoted by this Greek letter, which we call lambda. And so altogether we have an amplitude, there's a frequency of the wave, there's the wave speed, and then we have this wavelength. So it turns out that these three properties that I have on this slide are not all independent of one another. They're related in a very important way that we already hinted at in the last video. But I want to understand this in detail, and so what I have in the next slide is a very simple question where you're going to actually work out for yourselves what is the relation between wave speed, wavelength, and period, which is closely related to frequency. Okay, so to help us understand this, we have Baby Shark. So I'm borrowing this question from a course I taught a couple of years ago when Baby Shark was very popular. But just checking last night, I noticed that Baby Shark is still very popular. And in fact, just in the last few days, the number of people that have viewed the Baby Shark song is now greater than the population of the Earth for the first time. So that kind of blew me away. That means that, well, at least one person on Earth has viewed that video more than once. In some measure, this makes it the greatest musical composition of all time, but let's not think too hard about that. Interestingly, it only has 4 notes in the entire song. Okay, so let's talk about this question. So what I'm giving you is the wave speed of a wave, which is in this case a water wave. I'm giving you the wavelength of the wave, the distance between these two peaks. And I want you to figure out the period of this wave. So the way that I'm asking the question is, how long is it before Baby Shark will again be floating at the top of a crest? So the wave is going to move by. Baby Shark is just going to bob up and down. If you've ever floated in the ocean when it's wavy, you know that you don't really move along with the waves. You just bob up and down as the waves go by you. So that's what's happening to Baby Shark here. And we just want to know how long is it going to be from this time when he's at the peak of one of the wave crests until the next time when he bobs up to the top to the peak of one of the wave crests, because that is our definition of the period. So pause the video and take a minute to just work this out. Oh, I have the answer here already. All right, well, let's just go through it. In case you didn't already read the answer, let me just go through how we would do this calculation. Okay, so the way that we're going to do it is basically just use the standard relation between time, distance, and velocity. So the point here is that Baby Shark is going to go down and then bob back up in the time that it takes this wave crest here on the left to move from the current position over to Baby Shark. So the distance that this wave crest has to move is 3 meters, and the speed that it's moving at is 0.5 meter per second. And so the time it's going to take is going to be 3 meters divided by 0.5 meter per second, or 6 seconds. Okay, so the right answer in this case is D, 6 seconds. So let's just recall why we did that exercise. Okay, so the point here is that we could have done the same thing, whatever velocity I gave you and whatever wavelength I gave you, you could have done the same calculation in order to figure out how long it would take Baby Shark to get to the top again, and that number is the period. And so if we want to just write down something general here, what we could say is that the period t in general is equal to the wavelength, which is the distance that crest has to move, divided by the velocity, the speed of that wave crest as it moves along. And so this is our general relation between the period of waves, the wavelength of waves, and the wave speed of the waves. So this is extremely important, and it will be very useful to us going forward. It will allow us to make a lot of very interesting predictions. And so I want to just dwell on it a little bit more, and I'll just write it in a couple of different ways. So that was one way we could write it. Just rearranging that same equation, we could write the same thing as saying that the wave speed is equal to the wavelength over the period. Or another way we could write that, which is going to turn out to be probably the most useful form of this relation, is to rewrite the period in terms of the frequency. So this is lambda times 1 over the period, and so that's the same as lambda times the wave frequency. Okay, and so here we have that the wave speed is equal to the wavelength times the wave frequency. Okay, so this is going to be the most useful form of this relation when it comes to thinking about music, because we're often talking about frequencies of various musical notes, and those ultimately relate to frequencies of oscillations in various kinds of waves. Okay. Basically, one more thing I wanted to point out here. If you can't remember exactly what the formula is, I just wanted to point out a little trick that can help you if you're, ever stranded downtown without your phone and you happen to need to know what is the relation between wavelength and period and velocity, okay, and you just can't quite remember the formula. Well, you could either think about Baby Shark and work it out that way, or another way you can think about this is just to remember that the right combination is such that the units all work out. Okay, so velocity is measured in meters per second. And so if you want a formula that makes sense, what you want to do is take a quantity that is measured in meters and divide it by a quantity which is measured in seconds. Okay, and so that tells you that the only possible formula that would make sense, the only possible different rearrangement that would make sense here is that V equals lambda over T. So that's another example of something that I mentioned in a previous lecture, which is called dimensional analysis in physics. And that's basically just the statement that the formula needs to, the units on both sides of the formula need to match. Okay, so sometimes when I say, I think I might have said dimensions before, but I was basically just talking about these units. Okay, so I have one more question just to apply that and kind of continue to develop your intuition for this relation. The question is, if we have the same situation with the same wave speed, but now shorter wavelengths, then what will be the effect on the frequency of Baby Shark's oscillation? Okay. Is it going to be greater? Is it going to be the same? Or is it going to be less? So think about that for a minute, and then you can commit to an answer, and now we'll discuss it. Okay, so the answer for this question is that the frequency of Baby Shark's oscillation would be greater. And I want to take you through two different ways of understanding that. So the first way is just going to be using our formula. We have that the wavelength times the frequency is equal to, okay, I'm not very good at using this pen here, is equal to the velocity. It's trying to guess what I'm drawing. I need to adjust those settings somehow. So the wavelength times the frequency is equal to the velocity. And so basically, if the velocity is staying the same and the wavelength is getting smaller, then the frequency must be getting bigger. But let's understand it intuitively. So suppose that we just draw a situation where we had a shorter wavelength. So now I'm going to imagine this other wave where the wavelength is quite a bit smaller. It's actually about half as much as before. And so now we just think of the new wave moving along to the right at the same speed as the old wave. Well, since there are more wave peaks per amount of length here, if that new wave travels along at the same rate, then the frequency at which Baby Shark will encounter these wave peaks is going to be larger than it was before. So there'll be more wave peaks per second hitting Baby Shark, and so Baby Shark will oscillate up and down more times per second, and so the frequency will be larger. Okay, and just in case, oops. So here's a simulation. Hold on. I'm not sure if you'll hear it in using that one. Oops. Okay, here's a simulation with some waves traveling to the right. And what I want you to have a look at is this green bead right at the window, and look at how fast it's moving up and down. So that's a measure of the frequency of the wave, just the frequency of oscillation of that green bead. And now what I want you to do is just follow these wave crests as they travel from left to right. Okay, so keep your eye on those wave crests traveling left to right. And what I'm going to do is decrease the wavelength, but I want you to check that the wave speed is staying the same. So here we go. Okay, so if you were watching, the rate at which these peaks traveled from left to right didn't really change, but now the wavelength is a lot shorter than it was before. And now we'll go back to looking at this green bead at the window, and we see that it's oscillating up and down much faster than it was before. Okay, so let's just go back down to the longer wavelength. Okay, and again, hopefully you can see that everything is still moving from left to right at the same speed. And now again, the green bead has gone down to a lower frequency. Okay, so I think it wasn't totally clear that all the waves were moving at the same velocity when I changed the wavelength and made it smaller. It's a little bit hard for us to tell, but that is what is programmed into the simulation, so it should be true. Okay, so just to summarize this very important point that we learned in the last question, the conclusion is that if we have a fixed wave speed, then when I have a shorter wavelength, I'm going to get a higher frequency. And when I get a longer wavelength, I'm going to get a smaller frequency. Okay, so that's summarized by this formula, but it's also just conceptually, because if you're in this situation, those wave crests are going to hit you more often, and so you'll be going up and down at this higher frequency. So this is a really important relation when it comes to music. It ultimately is the reason why large instruments produce lower sounds, and we're going to talk about this in great detail in the future. So with your saxophones, the larger ones end up giving you the lower notes, or same thing with your strings. Your double bass plays lower notes than your violin. And so this is all coming from this basic relation between wavelength and frequency. So I just have one more question with Baby Shark, and it connects to the history graphs and the snapshot graphs that we talked about in the last video. So this is just the same thing, but in the context of talking about sinusoidal waves. So my question is, which of these graphs below represents the history, or the history graph for the duck, or the duck's vertical displacement as a function of time, starting from the time shown? So think about that for a minute, and now we'll talk about it. Okay, so what we want to think about is basically us sitting here and watching this duck as it bobs up and down in the water. And so what we can say is that starting at this time, the duck is in the equilibrium position. Okay, so originally the displacement is 0, so we're looking at either A or C as our answer here. But then as time passes and this wave moves to the right, the first thing that happens is that the duck goes upwards. So the duck will go upwards and then downwards and then below the equilibrium position and then upwards again. And so the correct answer here is this answer A, that this is the history graph for the duck. And so you notice that that is also a sinusoidal function of time. And just like in our last video, if we increase the wave velocity for the same wavelength, then that sinusoidal function would get squished and you would see essentially a shorter period and therefore a larger frequency. If we wanted to, we could also plot the history graph for the location of baby shark. And since baby shark is currently at the top of a wave crest, then the history graph for baby shark would look like this, where it would go down, hit the bottom, and then go back up again. So next time, we're going to talk about, again, thinking about waves, but now in the context of waves in fluids. So we just have to understand, what is actually waving when we're talking about sound waves in air, when it's just a bunch of air molecules moving all over the place. Okay. And we can also talk about sound waves in solids, and that will be related. There will actually be several kinds of sound waves that you can have in solids. The subject of thinking about earthquakes, there you actually have various kinds of waves in solids at the same time. So that's all for today's lecture, and we'll see you next time.